Hello everybody, welcome into another lesson. So today we are going to talk about the inverse and contrapositive of if-then statements. So earlier in the course we talked about if-then statements. So the original statement will read something like if P then Q. We've seen those, and we've even dealt with their converse, which flips the hypothesis and the conclusion around. It says if Q then P. That's the converse. And then we talked about biconditionals, which were if the original statement and the converse are both true, then you have what's called a biconditional statement. It would say P if and only if Q. But there are two types of statements to the original we have not yet talked about. They are statements of negation. One called the inverse. The inverse states if not P, then not Q. And then you have the contrapositive, which states if not Q, then not P. So the inverse negates the original the way it is. The contrapositive negates the converse. You could almost think of it contra, converse, and negates the converse, and then the inverse from the original. So it's also worthy of noting that the original and the contrapositive are logically equivalent to each other. So let's do some examples here of these. Alright, I'm going to make a statement here. So the first statement is, if I live in Los Angeles, then I live in California. Alright, so what we've got to do with the next few exercises, we're going to have the original statement. We're also going to write the converse of the statement, the inverse of the statement, and the contrapositive of the statement. So let's start with the original statement. If I live in Los Angeles, then I live in California. That's definitely true. Los Angeles is in California. That would absolutely be a true statement. Now, what about the converse? Let me write converse above here. So the converse of the statement would be if I live in California, then I live in Los Angeles. So the converse of the original statement would read, if I live in California, then I live in Los Angeles. Is this necessarily true? No, because you could live in San Diego, you could live in Sacramento, or San Jose, or Oakland, or San Francisco, or Fresno, or any of those cities, any other cities. So that's not necessarily true. So this would be a false statement, because you don't have to automatically live in Los Angeles if you live in California. Now, what is the inverse of the original statement? The inverse is going to be if I don't live in Los Angeles, then I don't live in California. So the inverse would read, if I don't live in Los Angeles, then I don't live in California. Well, it's kind of the same reasoning as the converse. I may not live in Los Angeles, but I could live in any other California city, right? So the inverse is false. Okay? So then, let's do the contrapositive of the original statement. Let's write the contrapositive out. The contrapositive would state, if I don't live in California, then I don't live in Los Angeles. So the the contrapositive of the original statement would read, if I don't live in California, then I don't live in Los Angeles. Well, that's true, because Los Angeles is in California. So if you don't live in California, you definitely don't live in Los Angeles. That would be a true statement. So you see from these examples here that the original statement and the contrapositive are logically equivalent. By the same token, you can also say the converse and the inverse are logically equivalent too. And I do have more examples here. I got plenty more. All right. A geometry related one. If the measure of angle 1, no, that's not right. Not quite there yet. If angle 1 and angle 2 are vertical angles, then the measure of angle 1 equals the measure of angle 2. So, this statement is, if angle 1 and angle 2 are vertical angles, then the measure of angle 1 equals the measure of angle 2. The original here. Is that going to be true or false? Well, that's going to be true because we know vertical angles are congruent. So that's absolutely a true statement. Now let's take the converse of the statement. Let's take the converse. If the measure of angle 1 equals the measure of angle 2, then angle 1 and angle 2 are vertical angles. So the converse of the original statement is that if the measure of angle 1 equals the measure of angle 2, then angles 1 and 2 are vertical angles. Well, let's think about this. That may be true. They very well could be vertical angles, but they could also be... What else could they be? They could be alternate interior angles. They could be corresponding angles. They could be congruent angles of an equilateral triangle or of a right triangle. So this statement is not necessarily true. They don't just have to be vertical angles. Therefore, it makes it false. Now, what would the inverse of the original statement be? The inverse is if angle 1 and angle 2 are not vertical angles. Well, let me abbreviate that a bit so I don't run out of space. Then the measure of angle 1 does not equal the measure of angle 2. So the inverse of the original statement is that if angles 1 and 2 are not vertical angles, then the measure of angle 1 does not equal the measure of angle 2. Let's think about that again. Well, what if they're alternate interior angles? What if they're corresponding angles? What if they're angles of an equilateral triangle or an equilateral quadrilateral or of a right triangle? Or you get it. They could be any other type of angle. So this statement is also false. It's not necessarily true that they just have to be vertical angles. Now, what about the contrapositive? Let's get into that. What does the contrapositive say? The contrapositive would state that if the measure of angle 1 does not equal the measure of angle 2, then angle 1 and angle 2 are not vertical angles. So the contrapositive states that if the measure of angle 1 does not equal the measure of angle 2, then angles 1 and 2 are not vertical angles. Well, that would be true, right? If they were vertical angles, they would be congruent. So this is absolutely true. They definitely can't be vertical angles if they're not congruent. So again, another example of how the original statement and the contrapositive are logically equivalent, and then the converse and the inverse are logically equivalent also. Okay, so what's next? If AM equals MB, then M is the midpoint of segment AB. So here's the original statement. This is just the original here. If AM equals MB, then M is the midpoint of segment AB. Would that be true or false? That would absolutely be true, because, well, by the definition of midpoint, you have two congruent segments, so this would absolutely be a true statement. Now let's go on to the converse. You're about to find something very interesting here with this one. If M is the midpoint of AB, of segment AB, then AM equals MB. Well, let's stop and look at this. If M is the midpoint of segment AB, then AM equals MB. That's actually true. By the definition of midpoint, that's actually true. Now, often the contrapositive, the contrapositive and the original are always logically equivalent, but sometimes, but not always, the converse will be too. If the converse is also logically equivalent to the original, in this case it is, then you can form, again, what's called a biconditional. That states that AM equals MB if and only if M is the midpoint of AB. That means that both the original and converse are true. Now what about the inverse of this? What is the inverse of the original statement? If AM does not equal MB, then M is not the midpoint of segment AB. So the inverse is that if AM does not equal MB, then M is not the midpoint of segment AB. Well, if AM did equal MB, M would be the midpoint. So this is actually a true statement also. The inverse is also true. So every once in a while, you'll have the converse and the inverse that agree with the original. Now, how about the contrapositive? What would that say? The contrapositive would state that if M is not the midpoint of segment AB, then AM does not equal MB. So let's think about this one too. If M is not the midpoint of segment AB, then AM does not equal MB. Well, that's also true. Because by the definition of midpoint, if M is the midpoint of AB, then AM would equal MB. If they're not equal, then M's not the midpoint. It's that simple. So after doing these a while, it's very tempting to want to say that the original statement and the contrapositive will always be true and that the converse and inverse will always be false. This is a prime example of why you can't always go by that. You have to take it on a statement by statement basis. And I got some more examples here. So the original statement is if a triangle is scalene, then it has no congruent sides. So this is the original statement that says if a triangle is scalene, then it has no congruent sides. Well, that's basically the definition of a scalene triangle. It has no congruent sides. So the original statement in this case is also true. Now, what about the converse? What would the converse have to say about that? If a triangle has no congruent sides, then it is scalene. So let's look at the converse statement. If a triangle has no congruent sides, then it is scalene. That's also true based on the definition of a scalene triangle. So in this case, the original and the converse are true. Now what about the inverse? The inverse states that if a triangle is not scalene, then it has congruent sides. So the inverse of the original statement is that if a triangle is not scalene, then it has congruent sides. Well, let's think about triangles. We're classifying them by sides. If a triangle's not scalene, then it's either going to be isosceles or equilateral. Those are the only other two choices. An isosceles triangle, as you know, has at least two congruent sides, where an equilateral triangle, all three sides are congruent. So this is actually true. At least two of the sides would be congruent if it has congruent sides. So that the inverse is also true. Now what about the contrapositive? So what does the contrapositive say? If a triangle has congruent sides, then it is not scalene. Alright, so the contrapositive is if a triangle has congruent sides, then it is not scalene. Well, the only other two types of triangles are isosceles and equilateral, and both of them have at least two congruent sides. The equilateral has all three sides congruent. So the contrapositive is actually true in this case too. So another case, again, where yes, it's true that the original and contrapositive are logically equivalent, and oftentimes you'll get the reverse result from with the converse and inverse, but not always. Sometimes they do agree. I have two more examples like this, and then I have 3 sentences that we got to draw conclusions from, then we're done for the day. So let's go ahead and do the original statement. If negative 2n is less than 6, then n is greater than negative 3. So here's a good algebra problem. If negative 2n is less than 6, then n is greater than negative 3. Is the original statement true or false? Well, by solving this inequality, remember, whenever you divide by a negative, you flip the sign. So this would absolutely be true. This is absolutely a true statement. Now, what about the converse? How about the converse of the original statement? The converse would say that if n is greater than negative 3, then negative 2n is less than 6. So let's look at this here. Plug in any value that's greater than negative 3. What about negative 2? So negative 2 is greater than negative 3, so you put in negative 2, you would get 4. You put in negative 1, you would get 2. Put in 0, you get 0. Put in 1, you get negative 2, so that's actually true. You can test your values here and find that the converse of the statement is true. Now, what would the inverse of the original statement say? The inverse would say if negative 2n is not less than 6, then n is not greater than -3. Now, here's especially with inequalities, what really gets people. A lot of people, when they take an inverse, if you negate a greater than or less than, it's automatically assumed that you flip the sign around. That's not always true. If -2n is not less than 6, it could not only be greater than 6, it could be equal to 6, right? We have to take that into consideration. And if n's not greater than -3, not only could n be less than -3, it could be equal to -3. So let's go ahead here, let's play with this. Let's just put n equals -3. If n equals -3 here, so if -2n is not less than 6, then n is greater than -3. Well, if n equaled -3, you would have 6, which 6 is definitely not less than 6, right? It equals 6. What about if I put in -2? If it's not greater than, which actually not greater than, let's put in -4 since it's not greater than. If I put in -4 for n here, that would give me +8. +8's definitely not less than 6, so this is also true. The inverse of the statement is also true. So what about the contrapositive? What would the contrapositive say? Sort of the same thing, but in reverse. If n is not greater than -3, then -2n is not less than 6. So if n is not greater than -3, then -2n is not less than 6. Well, we just kind of demonstrated it with the inverse. It kind of holds true with the contrapositive, so we can say the contrapositive of this would absolutely give you a true statement. And I do have one more example of this. Then we got 3 sentences that we got to reach conclusions about. Or try to reach conclusions about, I should say. Okay, this is a good one. If x squared is greater than 1, then x is greater than 1. Think about this one real carefully. If x squared is greater than 1, right, then x is greater than 1. Well, let's solve x squared is greater than 1. Which would have to mean it's definitely greater than 1. That part's true. But they also don't consider that it could be less than -1, right? X could also be less than -1. So this statement, the original, is actually false. This is a rare example of the original being false, because it doesn't allow for the fact that x could be less than -1. That would give you another x squared is greater than 1. Now, what would the converse say? The converse says if x is greater than 1, then x squared is greater than 1. Is that true or false? If x is greater than 1, then x squared is greater than 1. Well, that's certainly true. The converse is absolutely true. Now, what about the inverse? What would the inverse of the original statement say? If x squared is not greater than 1, then x is not greater than 1. Let's really look at this here. So, if x squared is not greater than 1, then x is not greater than 1. Well, if it's not greater than, that means it could either be equal to or less than. So, why don't we put in a 0 for x? Well, 0 is certainly not greater than 1. How about a -1? Well, -1 would equal 1. That would still hold true, but what if we put in -2 for x? Just what if we did that? -2 to the second power would give you +4, which is greater than 1. So we have that going for us. So not greater than 1, x not greater than 1 means it's either less than or equal to. So this actually would be kind of false, because this is a false statement for the fact that you can have x be less than 1 and still have x squared greater than 1. So the inverse doesn't hold up. It's absolutely false. How about the contrapositive? What does that say? The contrapositive of the original statement. So this is a rare occasion where the converse and inverse disagree with each other. So really the converse and inverse aren't entirely logically equivalent, but only the original and contrapositive are. But anyway, the contrapositive would state that if x is not greater than 1, then x squared is not greater than 1. Would that be true or false? Would that be a true or false statement? Well, okay. So not greater than 1. What if, again, we put in some values here? Let's put in some values. What if x equaled -2? -2 is less than 1, which would give you 4 would be not greater than or equal to 1. Well, that would absolutely be a false statement. The contrapositive still holds as false. So the only true statement we got is the converse, and sometimes you'll have that where only one of them's true. Alright, now I got 3 sentences here. We got to use additional given information to try to determine any conclusion. This isn't a simple true or false anymore, but it's still pretty simple. So let's see. Given, what's the given information? If it is not raining, then I am happy. So here's a logic statement. We're given, if it is not raining, then I am happy. Well, here's the first one they give us, the first additional statement. I am not happy. Alright, so they give you an additional statement with this. I am not happy. What conclusion can we reach, if any? Well, in this case, looking at it, if it's not raining, then I am happy. I am not happy, so, but here's the problem. There could be a multitude of other reasons that they're not happy. It may not be raining, but what if they just got the worst news of their life, or they went through something truly horrific? So really, we can't reach a conclusion out of this. There is no conclusion that we could possibly reach because there's so many other reasons they might be unhappy. All right, statement 2. It is not raining. They tell you in statement 2 that it is not raining. And you're given, if it is not raining, then I am happy. So this time we can reach a conclusion that I am happy. So to draw a conclusion, you have to be able to directly connect the conclusion with the hypothesis. The last one we couldn't because there's a multitude of reasons they could have been unhappy. But this one's clear. It is not raining. I am happy. What's the third statement? The third statement they give us is that I am overjoyed. So the third statement they give you, in addition to the given information, is I am overjoyed. Well, that's great. I'm glad they're overjoyed, but that has nothing to do, it may have something to do with the fact it's not raining, but we don't actually know that. They may have gotten the best news of their life, like they may have won the lottery, they may have just had a baby or something, or they may have won a car, who knows. But we don't really know why they're overjoyed, so we have to say no conclusion for this one. And then we have one more additional sentence with this statement. The fourth sentence is going to be, it is raining. So this time, they give you the fact that it is raining. Well, they give you in the original, if it is not raining, then I am happy. We have something we can base off the hypothesis now. We have a conclusion we can reach. What we're really given in the sentence is the inverse, which would be, if it is raining, then I'm not happy. So the conclusion we can reach is, I am not happy because it's raining. The conclusion we can reach is, I am not happy. Alright, 2 more sentences with given information, then we're done. Alright, so given. All my students love geometry. I'm not so sure how most of you feel about it. I can't blame you if you don't. That's okay. So we're given that all my students love geometry. Okay, what's the additional information they give us? In the first statement, Stu is my student. Well, they give you, for additional information, that Stu is my student. The original statement is that all my students love geometry. So if Stu is my student, we can conclude that Stu loves geometry. That allows us to conclude that Stu loves geometry. Alright, what's the next statement here? The second additional statement is that Luis loves geometry. So this time the additional sentence in addition to the given information is that Luis loves geometry. Can we conclude anything from that? No. Why not? Yes, we're given that all my students love geometry. It doesn't say only my students love geometry and everyone else hates it. Luis very well may not be their student, may not be my student, but that still doesn't disqualify him from loving geometry. So really there's no conclusion we can reach from this. So, hey, Luis, good for you. You love geometry. That's great. All right, what's the third statement with this? And can we draw a conclusion? Stella is not my student. Okay. So the third statement we're given, in addition to the given information, is that Stella is not my student. Can we draw a conclusion? Again, the given statement says that all my students love geometry. It doesn't say that my students and my students only love geometry and everyone else hates it. It doesn't mean Stella doesn't love geometry. She may not, but she might. So, no conclusion for this one either. And how about the last statement? The fourth statement is that George does not love geometry. Okay, so the additional statement we're given, in addition to the given information, is that George does not love geometry. Well, read the given. All my students love geometry. Well, George does not love geometry, therefore George is not my student. That would be the conclusion. George is not my student. Would be the best conclusion you could possibly reach. So you're probably starting to see how the inverses and the converses and the contrapositive come into play when trying to figure out these statements, because some of the additional sentences are in those forms. And I just got one more example with 4 additional statements and we're done for the day. Now we kind of already did one like that. Here's one. Given. So here's a given one. All senators are at least 30 years old. So the given information is that all senators are at least 30 years old. And if you know anything about the government or the Constitution, according to the U.S. Constitution, that's absolutely true. You have to be at least 30 years old to be a U.S. Senator. But let's see if we can draw any conclusions from the additional information we're given. Statement 1. Jose Avila is 48 years old. So pay attention to the additional sentence with the given information. Jose Avila is 48 years old. What does the given information say? That all senators are at least 30 years old. But it doesn't say that everyone that is at least 30 years old is a senator. So Jose Avila very well could be a senator, but also may not be a senator. So we can't draw a conclusion on this one. Just because he's 48 years old does not make him a U.S. senator. All right, what about the next piece of information? Rebecca Costello is a senator. I don't know if this is real or not, if there ever was a senator named Rebecca Costello. That may have been before my time, if one ever existed. But this given, the additional statement to the given is that Rebecca Costello is a senator. And the original given is that all senators are at least 30 years old. The conclusion is then that Rebecca is at least 30 years old. Because if she's a senator, that means she's at least 30 years old then. So we can conclude something out of that. Now, 2 more additional statements, then we're done for the day. So the third statement is Constance Brown is not a senator. So the third statement is that Constance Brown is not a senator. Can we draw a conclusion on that? Granted, the given said that all senators are at least 30 years old. It doesn't say that every person at least 30 years old is a senator, right? So just because Constance Brown is not a senator doesn't mean they're not at least 30 years old. I mean, I'm 38 and I'm not a senator. If I were, I probably wouldn't be up here doing this. So, no conclusion based on the information that we have. So, no conclusions possible for this statement. And then we got one more. The fourth statement and final one is that Lean Chain is 29 years old. Alright, so in addition to the given information, you have that Lean Chain is 29 years old. Well, clearly they're not at least 30, right? You have to be at least 30 to be a senator. So we can actually conclude that Lean Chain is not a senator. Okay, so after teaching this lesson, you're all probably wondering, well, where am I going with this, with what I taught today? Well, tomorrow, or the next lesson, hopefully tomorrow, we're going to get into what's called indirect proofs. Up till now, we've done direct proofs. The next lesson is going to be indirect proofs, which require kind of backwards thinking. So that's why we've spent so much time on original statements, converses, inverses, and contrapositives. It's going to require that kind of thinking to be able to successfully do an indirect proof. So stay tuned for that. I hope everyone has a great night. Take care.